Sir, we can't hear anything. We can't hear anything, sir.
Sir, please, we cannot hear you.
Okay, now?
Yes, we can hear you now.
Yes, okay. Sorry, so I just defined the complex number. If you didn't catch up, we are defining a complex number of being a number that will be referred to as Z, where it has two components. One is the real component, the other is what we call the imaginary component, and both are real numbers. Now we are going to define some operations on real numbers, very simple for addition and subtraction. So is it disturbing the light a little bit? Okay, so I think last time we defined, let me see where we stopped, complex. We defined the complex numbers. I think we even started with multiplication, right? But just let me do it quickly. So first of all, we are going to represent a complex number in the XY plane. So this XY plane, because it's a special XY plane, we will call it the complex or complex number plane, where by definition, we will this complex number or complex part or imaginary part will go here. Okay, so this one with the imaginary, this one for the real. So this is by default, by definition. So for instance, if I have a point here, let's say this point, and let's assume this is -3, 2, and -3, let's say, okay? So this point, and I'm going to connect this point with the origin. So this point here, it will represent the complex number 2 minus 3i, okay? So always the y component here, even though I represent it as an ordered pair, but by default it means that y component it goes to the y-axis. Okay. Now you see here some similarity with the two-dimensional vectors, right? So here, if you like, you can consider. We'll see that many calculations are actually follow the. Yes, please.
Yeah, online people can't hear you.
I said, I think one was writing. You can hear me or you can't? Someone was writing yes.
You can hear now.
Yes, we can hear now.
You can hear now?
Yes.
Oh, I see. Let me just check because I know what's the problem. Let me switch to the other mic. So let's pick a microphone. Microphone system. Media. I think now it's better, right? Is it better now?
The other one was better.
Okay,
The other one was clear.
all right. Okay, so the complex number, as I told you, you can think about it as a vector, and many of the operations are also in line with vector calculations, okay? So addition of complex number and subtraction are straightforward. So let me assume here I have two numbers, z1, let's say it's x1 plus I, y1 are the real and the imaginary components. And another number, let's call it z2, and it has x2 and y2 as real and imaginary components. And let's take another number, let's call it k, real number. Okay, given these three values here, then we define actually the addition here. I'm just going to use this same addition, and we will put the numbers here. Let me just put this one, x1 plus iy1 plus x2 plus iy2. The outcome of this is very simple. So here I will take the x component, add them up together. And notice that here I will be getting x1 plus x2 plus I add the y components again here similarly, and y1 plus y2, and I take I as a common factor. So here I will be having, if you like, I times y1 plus y2. So you see here two numbers in the standard form or Cartesian form. I added them up to get the number in the same format. Similarly, of course, the division, while the division here, you have to be careful about the order. So here, for instance, this operation here is commutative. Obviously, if you flip the numbers here, you will be getting the same answer. However, for subtraction, this is not possible. So you have to preserve order here. And here in between, you have plus. So this negative here, it goes here. So by the standard here, you have always plus, and then you have I, y1 minus y2. Okay, so this is a plus. And here, let's add multiplication by constant. Multiplication by constant is also straightforward, just similar to a scalar multiplying by a vector, as we did it before. So k x1 plus I y1. And here, of course, this k expands to both components here, and we end up of having k multiple of each of the components here. So you have I
K or Ki, whatever. So this is of course K1. Okay. So here it doesn't matter whether you multiply from the right or from the left. So these operations are straightforward. Of course, here if you divide or multiply by the reciprocal of a number, then you divide. For instance, I can divide by 1/2, meaning I will just divide each one by 2 and so on. Any questions so far? These operations? Okay.
The second one.
Now, yes, please.
Why is there plus for the Z1 minus Z2? Why is there a plus in the middle of the operation?
You are asking about this last step?
No, the subtraction.
This one?
Yeah.
This addition, you mean?
No, the subtraction. Why is there? Yeah, Z1 minus Z2. Why is there a plus in the middle of the operation?
This is the definition. This is the definition. You add and subtract component wise.
Okay.
So if you add the real part to the real part, imaginary part to imaginary part.
Okay.
If you subtract, let's do an example maybe at this stage before we move to the multiplication. Let's take K equals 3, Z1 equals 2 minus 4i, and Z2 equals 3 plus 2i. Okay? Then what is Z1 plus Z2? So I add 2 to 3 is 5, minus 4 plus 2 minus 2i. I hope it's clear for everyone. So what I did here is I added up the real components to get the 5. And then here, negative 4 plus 2, I got negative 2i. So you have to be careful with the signs here. Now, Z1 minus Z2 is equal to 2 minus 3 minus 1. Then let's see here, we get minus 4 minus 2 minus 6i. Okay? And if I multiply, let's say, K times Z1, let's say, so I will be multiplying, if you like, the 3 with 2 minus 4i, and this means 3 expands here, so I have 6 minus 12i. Okay? I hope with this example, it is clear. Is it?
Yeah.
Okay. Great. So now let's move to the multiplication. Now, before I move to the multiplication, I will just remind you of multiplying two polynomial or two first order polynomials. Let's assume I have x plus 2. I want to multiply it with x minus 3. Oh, sorry. So let me just move it a little bit. Maybe I will just move here. Okay, now, so multiplication of complex numbers. So before I ask you, if you want to what we call polynomial multiplication, it's similar to polynomial. Multiplication is if you add x plus 2, let's say, times x minus 3. You remember how you did that? Solve that at school? What's the outcome here? What is the output of this one? Okay, you multiply the x with x. Okay, so you get 2 terms, right? Add it up to multiplying this one with the first, with this one, with the second. You remember this? Okay, So here you will be having x squared minus 3x. Then you have here plus 2x minus 6, right? And then you just combine these and you are done. Here we're going to do this similarly, but before that, here there is something special with complex numbers, is that the fact that here we have this I squared equal to -1. This identity here is very important when we deal with multiplication and subtraction. And this is a real component. This is a real number, right? Okay. So let's assume here again, we have two complex numbers. Again, as always, z1 equals x1 plus I y1, and z2 equals x2 plus I y2. Okay. Now, at the beginning here, I will just put this asterisk to represent the multiplication, just to show you that this is a different type of multiplication. But in the future, I'm just going to write z1, z2 like we do with real numbers, even without a dot in between. So then z1 times z2 as multiplication is equal to, so x1 plus I y1. I'm just putting the corresponding values of the numbers I, y2. Okay? What we're going to do, we are going to multiply them as we did up there for the polynomial multiplication. So x1 will be multiplied with x2 and with I, y2. So what we get here is x1, x2. Notice here that this is I will put a dot here. This is real number multiplication, right? Because both are real numbers, plus x1 y2. Now here, no matter where I put the I, but let me just put the I here outside or to the right. Then I'm going to multiply I y1, and notice here, if you have the negative, then you just need to include it with this one and that one. Okay. So what I get here is, again here, let me take the I to the right, and put x2 ahead. I can do that because of commutative property of real numbers. Now, what is the last number I get here? Plus with I first. y1, y2, I squared, right? Because I have here y1, y2, and I have I times I, which is I squared, right? Now, remember that I squared here is equal to -1. So this will, not only it will become negative y1, negative y1, y2, but it goes to the real component of the outcome here, right? So here I don't have any complex values anymore because I don't have I. So I have I squared, which is a real component. So here, if you like, I will this will be negative y1, y2, because of this is equal -1. So the answer here will be x1, x2 minus y1, y2. And this is if I write it as the standard form, this is the real part, plus y x1, y1 plus sorry, y2 here, x2, y1, y. This is the outcome here. And notice that this is in a standard form. So if you like, this is the real part of the, this is the real part of the multiplication, and this is the imaginary part of the complication. Okay, any questions regarding multiplication? Okay, guys online, do you have any questions? Yes, go ahead, please. Because there is an addition here. You just add these two up, group them, and take I as a common factor. Now here the negative comes from the fact I have I squared. Here I have I, which is the square root of -1. Okay. Clear? Okay. Questions online? Okay. Now it gets a little
Sorry,
bit more. Yes, please. Go ahead.
could you please go back to the formulas for 1 sec?
Sorry.
Could you please go back to the formulas for 1 sec, please?
To the previous page or here?
Yes, please, to the previous page.
You mean this one here?
Yes, on the bottom, please.
Yeah. You just want to write?
No, just take a picture. Thank you.
No question?
No.
All right. Okay, so let's move forward to the one more complicated issue or more complex issue is the division. But before that, let me define the following, and we will be using a trick here at the beginning that is really very often used in the conjugate of, is it with G? I think it's with G, right? No, with J. Conjugate. Okay. The conjugate of a complex number. Now, this conjugate given a complex number, let's just call it in general Z equals X plus I Y and highlight this plus here. The complex conjugate of Z conjugate of Z, we will use the notation Z with a dash on top of it or a bar is defined as very simple Z conjugate equals to X minus I Y. So all I do here is that I negate the sign of the imaginary component. That's it. Okay. This is just a definition. Okay. So instead of plus here, I will have minus. If I have plus here, of course, it will become minus. And notice this goes only for the Y component, okay, for the imaginary component. Now, of course, here, of course, let's see some examples here, maybe different examples than I have. Notice that let's start with a very simple example. So here, of course, example, find the conjugate. Z equals, let's take the number 3, just the number 3. Is it a complex number, this one? It's a real, but we said that real, by definition, all real numbers are complex, right? Because complex number is an expansion. So this is obviously a real number with, we said that a complex number can be a pure real or pure imaginary. So in this case, it's a pure real. And notice that here by default, this is equal to 0 times I, right? So what is the conjugate here? 3 minus 0 I, which is 3. So for a complex number, because the conjugate definition, it didn't touch the real component, so it's the same, right? Let's take a pure imaginary number. Let me take the example here, maybe 12i. Z equals 12i, and this is by default this is equal 12 0 is the real component plus 12i, right? So z bar or z component is just minus 12i. Here I change the sign of the complex part. Okay? Now if I have any other number, then it's just, for instance, z equals 3 minus square root of 3i. Then z conjugate is equal 3 plus square root of 3i. Okay? So again, only it affects the imaginary part. Just switch the sign of the imaginary part. Now, why do we do this? By the way, I will list some properties, but you can think about it. If I take this again, some properties of conjugate operation or operator. Okay, some properties. Now, if I take the conjugate and then take it twice, what do you expect? Yeah, then you get. So let me just put it here. Maybe if I have z equals 2 plus 3 or minus 3i, right? Then I take the conjugate 2 plus 3i, right? Then I take the conjugate of the conjugate again. 2 minus 3i. So if I apply the conjugate twice, it's just like I will get back to the original number, right? This is what we call it a button. Okay, so if you apply something twice, you will be getting the same. It's just like negation, right? If you negate a number, because it's ultimately defined using the negation, so obviously it will also inherit the properties of the negation. Okay, so of course here, given how many numbers I need here, so given, let's say, z1 and z2 are complex numbers. Okay, so z, maybe I write it here down so I have more place. Z bar is equal to z. Okay, so if I apply this conjugate story twice, I will be getting the original number. Okay, now I will just write the operation, and then, or maybe I will just try to write the property here, and then we will just do it here to the right. What do you expect if I add a number to its conjugate? Yes? If you have, yes. So that you will be getting twice the real part, right? Twice the, why? Because by definition, the imaginary part once will be positive, the other will be negative, or vice versa, so it will cancel out. Okay, so at the end here, of course, here each of these here, so here you have z equals x plus iy. So by definition, z1 equals x1 plus iy1, and z2, this is just the breakdown of these three operations here, or three definitions. So this is here related to the assumption. Okay, so here what do we have? 2x y. So here let's just do it here with green here to the right. So I will be having z equals x plus iy, z bar equals x minus I. So if you add them up, this will cancel out and you end up of having 2x, which is the rule, what the rule is saying actually, right? Now, if we have the subtraction, now the subtraction, in the subtraction, I will be having here negative. So here negative, right? Then this will be negative, so this will be plus, this will be negative. So in this case, x will cancel out. I will be ending up of having twice I y. Okay? You see it? So if I'm subtracting z minus z conjugate, I will end up of having 2y1i. Sorry, y here. Of course, I didn't. 2y times I. Let me just do it here. 2yi. Okay? I hope it's here. It's clear here from the right-hand side. You will be having negative. The negative expands to x and y. So here it will become positive. So you have iy plus iy, and then the x will cancel out. Okay. So conjugate of x plus iy is, yes, exactly. If you have it negative in the original, you will turn it positive. Is part of your answer, of course. Okay. Okay. What is 0? Yes. Yeah, okay. You want you want us to do this for the negative? Okay, so z equals x plus iy is the original, right? Z conjugate is equal x minus iy, right? Now let's subtract them. So if you subtract them, you have z minus z bar equals to x plus iy minus x minus iy, right? So this minus will expand here. So you have here x plus iy minus x plus iy. So x will cancel out and you end up of having twice iy. Okay. Okay, now let's see some more properties. Actually, the most important property is the following. No, it's not the following, it's the last one. Anyway, what if I multiply? What if I multiply? Notice that here, because of the fact that I have, I don't know whether you know this equation of the complete square, where you have, for instance, we used it when the last, or the 2 weeks ago, when we had the equation of a half a circle. If you have x squared plus 9 or minus 9, sorry, you factor it, you have x minus 1 plus, right? So this is the conjugate of each other. So let me just write it here just to remind you. So x squared minus 9. You remember? So it's equal x plus 3 times x minus 3. So if you like, these two are conjugate to each other, right? Now here, if I'm multiplying, I will be getting similar behavior here, right? What if I multiply a number with its conjugate? Think about it. Z multiplied with its conjugate. What would we get? Sorry? 8 x squared yeah plus I squared multiplied by y squared, right? So I will just write it here, the outcome, and let's do it here on the, maybe here, this screen stuff here is just demonstration. So let me just do it here. I will be having here x plus iy multiplied by x minus iy, right? Correct? So I have here x squared minus xyi, right? Plus xyi, and here I have minus. Oh, so it's no. So here in the formula it's plus, right? This is plus. Okay. So here, because I have here y squared I squared, right? So here it's -1, so this will go here and it will become plus. So here I have at the end x squared plus y squared, while these two will cancel. Okay, so it's similar to this behavior, but the sign here, because we have the I as I squared, sorry, it will cause -1. You multiply it with the negative, you will be getting positive. Okay, so multiplying a number with its conjugate will result in this is a very interesting phenomena that we will be using very often. Notice that here to the right, this component here, it's purely real. So this is an important, so here this outcome here, it's a real number, because the multiplying the number with its conjugate, the number, the imaginary part will cancel out. Okay, and this property we are going to be using later. Now the other two properties are luckily straightforward. If I have the conjugate, you can just find it out. Z1 plus Z2, if I add them up, then take the conjugate of the result, is just like taking the conjugates and adding them up. And the sixth property is the multiplication, and this is Z1, Z2. Okay, now this property here, this property is a very important property, and in fact we're going to use the technique in short, sorry, in a short technique that is also that will be used in evaluating some specific limits that we will solve maybe later in this course, and in particular in the next course. Okay. Questions so far? Questions? Okay, now we turn to division. Division becomes a little bit more, let me say, not complicated, more I will show you how to do it using the standard form. It will become complicated when we want to do it entirely using the standard form, but if we do it using other forms, it will be straightforward. Luckily, we have some other forms like the polar, etc., and their multiplication and division are straightforward. Think about, we just defined the addition, sorry, the multiplication, and then we said that multiplication once is, you saw it's not that straightforward. So if you multiply, you will be getting 4 terms. Then if you multiply again, so imagine you want to evaluate the complex number to the power 4 or 5 or 6 or whatever. Okay. Now, division of complex numbers. Okay. Now, in division of complex number, we do really have a problem because in mathematics, it doesn't make sense if I have I in the denominator. It doesn't make sense if I have I in the denominator. So let's assume again, as always, Z1 equals X1 plus IY1, and Z2 equals X2 plus IY2. Okay? So what does it mean? We're going to use either the normal division, which one I use here, or just a dash. Let's use the dash because we will need it. So Z1 over Z2 equals to X1 plus IY1. Okay, if I want to write this in the standard form, I have a problem. Why? Because I have I here in the denominator. And this is in mathematics is just something that doesn't make any sense. So what to do here? Remember the property number 4 in the previous page? Okay, so the way out here is we're going to use the technique. Consider this number here, let's call it Z2. We will multiply and divide by the same number. This technique is used very often in mathematics. If you just are deadlocked somehow and you want to get out of this situation, so we will multiply. You always you can multiply and divide by any let's say any value, because it's just like multiplying by 1. It will not change anything. Okay, so here X2 minus I Y2, and I will be dividing by the same. I will tell you now. You see here this number here, it's nothing else. This one is the conjugate of Z2. Okay, now why I did that? Because obviously, using rule number 4, if I multiply out the denominator here, I get rid of I, so I don't have any complex values anymore. Okay, so this one here is Z2. Guys in the back, just share your comments with us, maybe others. Yes, do you have a problem, question? No question? Okay, I just multiply and divide by the conjugate of the denominator. That's it. And I can do that because it's just like multiplying by 1. And this trick we are going to be using also. I will just, even though it's premature, I will tell you now, in many cases, if you have limits of something, the square root of, and it's getting, by the way, it's also in line with the rule I just showed you. So the complete square, x squared minus 19, 16, whatever, you can just break it down into x minus 3 times x plus 3, for instance. And if you go it back, use it backwards, it's just similar to this one here. Okay, now what is the denominator here? And this is equal to x1 plus, let's just write it as is now. We will multiply it, x2 minus IY2. And here in the denominator, what do I get? Yes? X1 in the denominator. x2 squared plus y2 squared. Yeah, just you go back to rule number 4. x2 squared plus y2 squared. And notice this is the most important thing, and why we use this trick here. This is completely a real number. So here in this case, multiplying and dividing by the conjugate of the denominator, it helped us out of this dilemma to get rid of the fact that we have I in the denominator, which is not allowed. Okay? So maybe let's just check the students who are following online and then see exactly. No, hold on. It's plus. Mehul, is that? Okay, it's x squared plus, not minus. Because I hope you got it. Yeah, because here this is a plus because you have minus y squared I squared. Okay, great. I agree. Shadow, which shadow? Let me see. Oh, now it's better. Okay.
Yeah, that's better. Thank you.
Okay. Now let's demonstrate this in an example. Okay, so example here, it says divide 2 plus 5i over 4 minus I. Okay, so usually evaluate or simplify or whatever. Okay, evaluate. Now what we do here is 2 plus 5i over 4 minus I multiplied by 4 plus I. This is actually the trick here. You just have to multiply and divide by the conjugate. Notice that this here, it will not affect the to shut it down this. Okay, it will not affect the outcome because it has the value of 1 ultimately, and it's just like multiplying by 1. Okay, now of course here in top here you will just continue and evaluating this as x squared, sorry, x1 squared. Anyway, so x1, x2, and so on, just like we evaluated it before. So we will do it for the example here. So let's start here with the denominator. What is the denominator here? 4 squared plus minus 1 squared. Notice here that x is here minus 1. It's in the original number, not in the conjugate. Okay? Yes? Minus 1 squared. Not minus 1, minus 1 all squared. Okay? So be careful here because this is, if you like, this is my y x here, sorry, and my y here is equal -1. Okay, you got it? Now here up there I have multiply 4 plus I, just regular multiplication. So here in the denominator I got 17, right? So this is equal to, here in the denominator I got in. What do I get in the numerator? 2 times 4, which is 8, right? Plus 2i plus 20i. And here the final one, I got 5i squared, right? And this is equal to 8 minus 5 plus 22i. Okay, so this is, notice that here, maybe I need to explain this. This one here, it's -1, right? I squared. It goes to this, it becomes negative, so that's why. And I will take this to the real component here. Okay, and then ultimately I have now you see here what I do here. 3 plus 22i over 17. Now if I want to bring the ultimate value here in the standard form, I need to split the real part and the imaginary part, so I will just write it as 3 over 17 as the real part plus 22 over 17 times I. And this is you can say this is in the standard form. This is in the standard form. Now, of course, you think about it, if we have some more complicated addition, multiplication, or no need to make pictures. I'm going to upload the script later today. Okay, so what I was saying is the following. Imagine if you have more complex multiplication or multiplying and then adding and then dividing and so on. So this is really a little bit harsh here if you are using the standard form. And then even it's worse if it gets to evaluating the roots. I told you at the beginning of this course that there is fundamental theorem of algebra that says that a number, it says that a polynomial with degree n has exactly n roots under the complex number. So that means here, if you have something, maybe this is just on the side, if you have something like x to the power 5 minus 1 or plus 1 equals to 0, or let's just say minus 1, yeah? Then you would say, come on, this has only one root, right? Which is 1. This is true under the real numbers, but under the complex number, so here you have x to the power 5 equals 1. Where do the other 4 values come from? Okay, so according to this theorem, under the complex number, this has four roots for sure. 4 more roots. It has all in all 5 roots. Obviously, 1 is the real number. Okay, and further also, maybe at this stage I will tell you 2 things. The first thing, whenever you have complex roots, you will be having always the conjugate. So it means that the complex roots come always in twins. So if you have one value of such an equation is a root or a solution of this equation, then you have for sure the conjugate. So that's why here I have 1 real number as solution and 2 pairs of conjugates, if you like, that are the other 4. And I will remind you on this formula because we will need it today. But before that, geometrically, what does the conjugate stand for? What is the geometric interpretation of conjugates? So let me just remind you. Let's assume I have a number here. Okay, let's say this is 2 plus 3i, right? What is the conjugate here? Notice that the real part will remain the same. So I will be having the real value, so x, but the y value will be negated, if you like. So what I have here geometrically is nothing else than a reflection, no, of the number around the y-axis, the x-axis, right? Just as the reflection around the x-axis. If I have the number here, it's picture, if you like, or image under the x-axis. If I have it here, it will be here. Okay. So this is just the geometric representation of conjugate. Another thing that I just wanted to remind you, which is closely related to complex numbers, and I said I think this is one of the things that we talked about very often: roots of quadratic equations. I never memorized that, but I try to. Ax squared plus bx plus c equals to 0. You remember this from school? We have roots, let's say x1 and x2. You remember this? This is equal to, remind me what was this, x1, x2, minus b, is it minus b? B squared minus 4ac over 2a. Okay, now we are actually there. If you remember, now imagine that this amount, if it's greater or equal to 0, then you have real solution. Okay. If this is less than 0, then you are in the complex numbers. Okay. If this is less than 0, that means you have a root of a negative number, which will go definitely in the complex roots. Now here, what does this plus minus mean, which is the square root value? What does it mean? I hope you find the symmetry here with the conjugate, right? It means here that here, if I have a negative root, I will be having something with I. Once I will take it positive, once negative. So I'm taking the conjugate, the number as well as its conjugate as a root. So that's why this is the remark I just made before. Wherever you have odd degree of polynomial, then for sure you will be having one real number or 3 or whatever, and you will be left with an even number of roots in the complex numbers, which is each of them comes as a pair of the number and its conjugate. I hope this remark is clear. Is this clear? And if you look at the worksheet number 4 or 5, we have 4. I think the last or shall we take an example here maybe at this stage? Shall we take an example? So for instance, give me a polynomial where this will become negative. B squared minus 4rc. So we need to take either a or c, very large. So let's see 2x squared plus x minus 5 or plus 5. What is b squared here? 1. This will work definitely, or okay. So you have to help me out with this one. So what are the roots here? This is equal to 0. So the roots here, x1, x2 equals to minus b, which is minus 1, plus minus the square root. What is b squared? 1 minus 10, right? No, 40. 40. For AC is 40 over 4, right? Okay, you see here, so here we have x1, x2 equals to minus 1 over 4. Let's break this down. Plus minus square root of 39 negative over 4. But we said that this square root of 39, negative 39, this is equal to the square root of 39, which is real number, times I. If I just take the square root of negative 1, right? So the roots here, the final answer here, roots, let me just break them down. So minus 1 over 4, let's say this is x1, plus square root of 39 over 4i. I hope everyone understands where this I comes from. This is the square root of negative 1. And the second one is negative 1 over 4 minus square root of 39 over 4i. And notice that these are conjugates, right? So if you like, x1 conjugate equals x2, and x2 conjugate equals x1. So they have a conjugate relationship to each other, because only the sign of the imaginary part is different. All right. Okay, so this is now. Okay, guys online, regarding the roots, everything clear? Okay, now before we go to the break, I will just like to solve some examples with you, some solved examples. Let's see. Okay, so I have a list here of some nice examples, but before that, let's start with solved examples. Let's start with something very, very simple and basic. So what is the square root of negative 16? So we write it as negative 16, right? Times the square root of negative 1, which is square root of 16i, right? And this is, if you just want to take the positive part, it's 4i. It could be also plus minus 4i, okay? Because the square root of 16 is positive or negative. Okay, so this is a simple, straightforward calculation. Now here, let me see what other examples. I have here really very interesting examples, and I will just give you a couple of seconds to try to find out. Okay, so usually this says simplify the following. So simplify 2i plus 3i, which is straightforward. Here I don't have any real component, right? So what do you think? 5i. Okay, so if you add two numbers that are purely imaginary, you will end up of having a number that is purely imaginary as well. And if you have, so here simplify actually goes for all. So if I have here, let's say, I don't know, 16i minus 5i, very simple, straightforward, just to make sure that you understand the arithmetic behind that. 16i minus 5i, you get 11i, straightforward. Now let's see multiplication. 3i times 4i. This is 12, right? I squared. Okay, so here I just left the multiplication, and this is equal to negative 12 because I squared equals to negative 1. Clear? All right. Then we go to now I didn't mention that, but you can think about it as if I have three numbers and I'm going to evaluate the outcome of multiplication of these numbers, it's associative. That means I can just combine any two numbers and then evaluate the result. So let's see here, I times 2i, and I have here negative 3i, let's see. Okay, so here, if you like, I will just evaluate either the outcome of multiplying the first two. Please go ahead and try to evaluate this and let me see what you get. What did you get ultimately here? So 1 minus 3, and where is the negative gone? Where's the negative gone? So you have here 2. Let's evaluate these. 2i squared, right? Times negative 3i. And this is equal to negative 2 times 3i. Sorry, negative 3i, and this is plus 6i. This is the answer. Okay, so good that all of you anyone who didn't get the right answer here, straightforward. Okay, so let's see the guys online. Okay, great. Okay, let's move to some addition, and so I admit these are some of them. They might look a little bit trivial, but nevertheless, just to make sure that you got the theory behind that. So 2 plus 3i plus 1 minus 6i. So this is straightforward. So you have 2 and 1. So again, you add the alike components if you like. So 2 with 1, so you get 3. And 3 minus 6, you get minus 3i. Okay. So here you just add the alike components and you are done. Okay, subtraction 5 minus 2i minus or minus 4 minus I. Okay, again here the same. Now you have to be careful to the negative, right? Huh? What is this here? I got you something. I don't know, there's something wrong here. No, anyway. So what do you get here? 1 or 9? 9. Then, oh, hold on. Minus 2i plus I. Minus I. Right? Okay. Now the I don't understand this. Anyway, so let's turn to multiplication. Now here, this is a little bit. So multiplication 2 minus I times 3 plus 4i. So what did you find out? So other answers? Okay, let's do it. So 6, 2 times 3 is 6, plus 8i, right? Minus 3i. This one here plus or minus? Minus 4i squared, right? And we said this I squared becomes negative 1. And with this, it will become positive. So you have 4 plus, so you have 10. 6 plus 4. Now, I have here 5i, right? Is it 5? 8 minus 3. 10 plus 5i. Okay. Okay, now let's do some division here. Okay, so 3 over 2 plus I. Simplify 3 over 2 plus I. So, what to do here? Multiply by the conjugate and divide. What is the conjugate here? 2 minus I, 2 minus I, right? So this becomes 2 squared plus 1 squared, right? And here, notice that here no need to carry out the complex number multiplication because I have just a scalar multiplied. So here I have 3 times 2 minus I. And this is equal to 6 minus 3I over 5. I can split it here as 6 over 5 minus 3 over 5I. Okay. Now we will have couple of I to the power 12, I to the power 13. I or 12. So what do you think? I to the power 12? What is I to the power 12? What do you get? And 13? 13, what do you get? Negative? Well, I will just remind you with some basic rules. I told you at the beginning there's something that I would want you just to refresh your memories about the exponents and some simple logarithmic equations. So let me just remind you, if I have b to the power n plus, multiplied by b to the power m, what is the result of this one? N plus m, right? Okay. B to the power n over b to the power m, n minus m. Of course, here b to the power m is 0. Okay. Now, if I have a number p to the power n all to the power m, n times n, right? Okay. So these rules we need to apply here. Some in the other direction, of course. So anyone has problem with these rules here? If you have a base here, same base, multiplication, you add up the exponents, division, you subtract the numerator exponent from the denominator. So this is multiplication here. And this is division. Okay. Now let's go back to this, because if you understand these rules, it's straightforward. Actually, this simplification here. So first one here. Now we know I squared, right? So let's try here, if you like, to simplify this using I squared. So if I have here I squared and use the last rule there in the reverse order, what do I get? So I squared to the power 6, right? And this is equal to -1 to the power 6. And -1, I hope that everyone realizes this fact that -1 is actually, you remember when we talked about the determinants in the previous class, I told you that the original formula of Leibniz was alternating -1, +1, -1, +1. Actually, to generate negative and positive alternatively in mathematics, we use this rule that -1 to an even power always +1, to a -1 to an odd power it delivers a negative, right? So in this case, you just have an even number and then the outcome here is +1. Okay. Now in the next one, obviously here we don't have an even, or so we can't get I squared here. So we need to split it. So this is I to the power 12 times I. Because here I just use this rule in the reverse order. This rule here in the reverse order, okay? So this is 13. So I get 12 plus 1, okay? Anyone has problem with this trick here? And then from there, I take, so here I have, this is 1. I just evaluated in the previous step, and this is going to give me. So as you see here, 1 gives me a complex, a pure complex, and 1 resulted in a pure real, okay? Now, luckily, as I told you before, we don't need to do the whole arithmetic always in using the standard form, and that's why we will use the so-called polar coordinates or polar form of complex numbers. Now you just remember that I said at the beginning of this section that you can think about the complex numbers as any complex number here. You can think about it as this is z. If z equals x plus I, you can think about it actually as the ordered pair, where this is x here. So this is x, this amount here is y, and this here, if I call it r, and this is theta. So just like we did for the first or the previous section with the two-dimensional vectors. So here you have this coordinate here, x, y, where always y refers to the imaginary part here of the complex plane. Now, what is r? So polar coordinate of a number z equals x plus iy is given as, first of all, r, or sometimes it's just called the magnitude of z, if you like to refer to it as a vector. So here just square x, square y, very simple, you are there. And this is always a magnitude that is greater or equal to 0. And what about theta? Now you see here theta, this is a right triangle. Now tangent theta is y over x, right? So if you take the inverse of that, you have the angle. And again, here you need to be careful to two things. Okay. First thing is that starting with this number, you need to let's say determine which quadrant the number is located, because we saw that if x is negative, y is positive, different signs, then you end up of having the point either in the second or the fourth triangle. How to resolve this issue? You go back to the original point, whether it's negative x over y or negative y over x. This is important, like we did before. And the second thing, as I keep telling you always, you need to just make sure that the units on your calculator are degrees or radian, depending on what you need. Okay, so pay attention to the scale of your calculator. Usually it's either degrees or radian. Okay, let's stop here, and after the break we will see that luckily we have this and another coordinate that we call the polar, and they simplify things a lot when it comes to multiplication, division, exponents of complex number and so on. Okay, so let's take a break for 15 minutes. Yes, please. No, actually, this is a makeup for yesterday, because yesterday we had a holiday. I don't know whether you got an email from Miss Verena. So the idea is this. Please just hold on a little bit. This week we had the holiday yesterday. Next Wednesday we have the job fair. So that's why Mr. Wolfgang and I thought of just making up, at least rescuing one of these sessions. So today, if you like, this is the class of Wednesday combined with the class of Thursday. So that's why we started with a normal lecture. We're going to have 2 lectures, and the last session we will just have a look at the worksheet. Okay. You have chemistry. What are you? Oh, you don't take informatics. Okay, no problem. I will repeat it in 2 weeks, okay? Because next week we have, or you know what? We can meet on Thursday if you like. Only the PPE students, I can repeat it on Thursday, okay? For the tutorial, okay?
Quick thing, when we were looking at the divisions, I understand that if there's I in the denominator, then you would flip it. And
Yeah,
times
yeah.
To simplify, that's fine. I understand that. But what I was struggling to understand is how I ended up with -1. So I understood that where the 4,
Yeah, -1 is actually the coefficient of this, and if you don't have the number, it's by default 1.
okay,
Okay.
don't have the coefficient by default.
Yeah, it's by default 1, and the negative here. How will you interpret that? Okay. What is the value of x in this formula? It's 4 is y. Sorry, what's the value of y? 4 equals to x, and -1 is the x component. So you square the y component.
Okay.
The rule says square the x, add it to the square of y. Okay, everything is clear. Otherwise, yeah.
I didn't get the equation. How do I get this one?
This is a rule here.
Rule here.
This is a rule for.
Y is -1 and plus minus. Is just simply I just put a number of it.
You put the coefficient. So this is a rule for evaluating the quadratic equation. Okay, this is a rule. So a here is the coefficient of x squared. So in this example, a is equal to 2, b equals to 1, and c equals to 5. You just plug it into the formula. Okay, so this is the rule. Let's continue, guys online. Can you hear me?
Yes, sir.
Okay, so PPP class, they have, it's not scheduled. Anyone here, PPP class? Usually they don't have chemistry today, right? Sorry? Yeah, but normally you have at this time informatics, right? Okay, so again, so polar coordinates. So we said if we have a number, complex number in the so-called standard form, then so C or R. This is the polar coordinates. Okay, and both are actually parallel to, not parallel, sorry, equivalent to each other. So that means any point on the complex plane can be described as either a polar coordinate or either a polar or the standard or Cartesian coordinate. Now, why do we need this coordinate for? As I told you, this is much easier to evaluate multiplication, division, and exponents using this. And this is our next section. Okay. Now this section is a little bit sensitive, so we will try to solve examples. Powers and roots of complex numbers. Now this section requires the fact that you are capable to transfer a number from standard or Cartesian format into polar and vice versa. So here, if you like, there is a two-way equivalence here. So if you have a number in this format, you just square x, square y, add them up, take the square root. You have the magnitude, just like vectors, and then taking the tangent inverse of y over x will give you theta either in degrees or in radian. And as I told you here before the break, you have to be careful to which quadrant this number belongs. And this is simply according to the coordinates as we saw for x and y. Okay, now we have a very powerful this is D with apostrophe, de Morvier. De Morvier's rule or theorem. Okay, here, if we want in the polar format to write Z, then we write Z here as a polar format R, which is this amount here, times cosine theta plus I sine theta. So this is the polar corresponding. So we need to find R, to find theta, and then put it in this formula to find the corresponding polar format. Now, De Morvier's theorem, luckily, it helps us to evaluate exponents of complex numbers very, very easily. So, assume we have a complex number in polar coordinates. Let's say U equals R times cosine theta plus I sine theta. So the first component here is cosine is the real times R, and the second is sine times R. So this comes actually immediately from this. We just try to do it here, maybe in red. So if this is R, this is R, this is theta, this amount here, the X component, is just R cosine theta. And this component here, which is the Y, it's just R sine theta. Okay? So this is where this formula comes from. So now, as you see here, as you see, if we want to evaluate, let's take a very, very simple example here to show you, just to demonstrate how powerful the De Morvier's rule is. So if I ask you to evaluate the following: 2 minus 3i to the power 4. Okay? If I ask you to evaluate this amount here, or this term, what would you do with the tools we have so far? What would you do? Imagine you have a quiz and you want to evaluate this. What would you do? This is 2 minus 3i times 2 minus 3i, right? Times 2 minus 3i. So it's a little bit. Then you might use your IQ and say, well, this is the square, right? So you have, of course, the choice to multiply this out, and then you have it once, twice, and then the result, another one. Or you might say this is equal to 2 minus 3i squared, all squared, right? Then you evaluate this amount and you square it. Okay? You think you will manage it? Okay. 100%. Now, I am sure 100% if I like you 2 minus 3i to the power 98, for instance. Same thing? So how many days you need? So, are you still here? Up? Really? No problem. No problem. No, this is very important. Actually, evaluating the correspondent polar coordinates of a complex number, and later, of course, very easily the exponential, is essential here because this will help us with the theorem that I'm going to just introduce shortly. Straightforward to evaluate even more complicated exponents of complex numbers. So imagine here you have this to the power 4. You might manage to do it using by breaking it down into this form. Okay, then you will apply, just multiply this out and then square the result, sorry, to get, if we call this number z to the power 4. Now if you have it to the power 98 or 999 or whatever, then it gets, of course, very complicated, right? Now the way out of this, there was French mathematician, his name de Morvier. He came up with this rule, and n is actually a natural number. So then u to the power n equals to, I will just r to the power n multiplied by cosine of n theta plus I sine n theta. You see how simple is that? So I'll just highlight n here. N is the power here, which is a negative number, and then okay. Guys online, questions? Double square, okay. I can't hear anything. Still, you can't hear anything? I think now you should be able. We can hear but low. Oh, okay. Now I have to just make sure that microphone should be okay actually. You can hear clear now? Okay. Okay, how to use this theorem, this very powerful theorem. Now I want you to let's see an example here. Okay, use de Morvier's theorem to evaluate negative square root of 3. So this is an example. Use to evaluate this square root of 3 minus square root of 3 plus I to the power 6. So here let C equals this number.